Good evening, everybody. Well, Bruno, I think we need Madison Square Garden next time for you. We've sold out.
Stand back. Yeah.
Full house. Welcome to January's Astro Talk, first for 2025. And we have talking tonight on the telescope and technologies. The history of telescopes will be Bruno Zielke, who's giving us a presentation. Bruno's an ASV member who has a long history with the Society and is very passionate about cosmology and astrophysics. Gives a lot of talks to UA3 schools as well, don't you? Is it? Yeah. And is here tonight, as always, to share his knowledge with us. Before we begin, though, I do want to let everyone know that tickets for the Messier Star Party are active and on sale. If you go to the website, you'll see the link for the AC members. If you log into the AC website in the members area, you'll see there is a code for your discount to get you cheaper tickets. And so tickets are on sale. They're booking up fast as well. What else? We've got 2 weeks from now, or a week and a half actually, out in Hamilton. We have a public viewing night out there, which is free to the public as part of our Hamilton section to sort of grow astronomy in that region. We also have the Gippsland Star Party on the last weekend of March. Tickets are available for that as well. I think Star Party wise, that about does us until the middle of the year. I hope everyone had a lovely Christmas break and a good New Year. And we're all looking forward to some clear skies and some fun nights of astronomy. Are you clapping for me? Oh, clapping for clear skies. Yeah, clear skies during the day or at night? Yep. Don't be selfish. Don't be selfish. Clear days, clear skies all night round, except for when there's a full moon, then it can rain. All right, well, without further ado, following Bruno, actually, we will have a quick presentation from Ken, the head of Lone Telescopes, who's going to give us an update on the Lone Telescope program, whilst Bill sets up for his What's in the Sky. So we'll kick it off first with Bruno, if you'd like to come up and...
I'm wired up. Am I on? Okay. Lee. Oh, thank you, Tom. Okay. What's happened here? It's playing tricks with me. What did you do to me, Lee?
It's in presentation mode. You have to just push the arrow.
Right. Okay. Quick sip of water. Okay. Good evening, everyone. Here gathered at the Mueller Hall, and welcome all those who are watching this talk on the website, on the web, as it is streaming live. Now, everything we know about the universe is via some kind of radiation that comes towards us, whether it be friendly, visible light, or ultraviolet, or X-rays, gamma rays, or whatever. Everything, all the information that we gather about the internet, about the universe, comes to us in some form of radiation. So the telescopes are our eyes and ears, extended devices, which allow us to capture this information and then, of course, analyze it and make some kind of sense of it. So today we're going to talk about telescopes a little bit. Every time I pass this projector here, I go blind. Okay. Right. Most telescopes are built for a specific purpose. I have to stay out of that beam. They are grouped by different frequency range. What it means is that if you want to observe a visible light, you don't build an infrared telescope. They come in, initially they came in two varieties, mainly as reflectors and refractors. Now, in your camera, you have lenses which suffer from all kinds of optical aberrations, color, barreling. As the light passes the aperture, it causes. I'm an amateur photographer, so I'm fairly aware of that. So when it, okay, I'm running ahead of myself. Yes, so optical come in these two varieties. And then I'm going to talk about the square kilometer array. This started off as an independent project fired by Australia, where we anticipated to have international funding for a whole series, thousands of telescopes based in South Africa and in Australia, but we've built our own prototype, and it is called the Square Kilometer Array. In actual fact, the telescopes can be spread over 30 kilometers and further to make a much larger telescope, as it were. We only talk about gravitational wave telescopes. I'll explain a little bit about that. And then both earthbound and space telescopes. The one thing I'm not going to talk about is amateur telescopes, because you know more about it than I do. Okay, so the refracting telescopes, I have a pointer here. For those on the internet, I'm pointing towards the, it's actually working, refracting telescope. They use lenses to produce images. And then Newton came along and built a reflecting. He was the first one to build a reflecting, I'll show you a diagram in a moment, a telescope where light comes into a tube, it is reflected from the mirror into another mirror and then into an observational loop. So he was the first one to build that. And then there are compound telescopes which use combination of both. And then we have a different family of telescopes which are not really amateur. They are institutional telescopes, and they are built for specific purpose once again. And then we have gravitational wave telescopes. I use the word deliberately, not gravity waves, gravitational waves. There's a vast difference in that, and I won't go into the physics of that. Today, you're going to have an easy time. This is all about telescopes. Okay. So I've read on the internet that the first lenses apparently were built 75 years before current era. I don't know what they built them out of, because glass was not really invented then. So I'm not sure how reliable that is. But the Dutch are actually attributed in terms of having built the first lenses. They didn't build a telescope. It befell to Galileo to build the first one. And as you can see, it's only just over 1 meter long. And he was the first one to make astrophysical observations. And he really upset the establishment of the church, because at that time, in the Middle Ages, everyone believed and was told to believe that Earth is the center of the universe, and behold, if you're not, and if you don't agree with that, you get burned at the stake. So he discovered that the moon was not smooth and perfect as the current wisdom of the day had. It actually had valleys and mountains and all kinds of rough spaces, just like Earth does. He then turned his telescope towards Jupiter, and he discovered that the moons circle around Jupiter. Whoa, that was news. Everything surrounded Earth in the past. And now he discovered that that is otherwise. And that suggests that Earth was not the center of the universe. He discovered many other things. I won't go into that. And that completely contradicted the model of the day, which was held in great esteem by the church. So the church asked Galileo to deny the truth of it. He had to recount his findings publicly, at a public statement, and that saved his life. And he was confined to house arrest for the rest of his life. All his books that were in possession were burned, and that's the way things were done in those days. Nevertheless, some of his writings have survived, which is why we know what had actually happened. I'm going to be crossing this up and down all the time. Okay. And then came Newton. You can see it's not a very large telescope. It's about 33 centimeters in diameter of the mirror, and it was no doubt built of wood and had a copper mirror, which tarnished very, very quickly. So that wasn't very good. I'm not sure whether Newton built the larger one, and I didn't find any information about it, but the next built one was 150 millimeters, that's in diameter, which was a little larger. And there you have it. The light comes in here, is focused by that mirror, reflected of another mirror here, and goes into the observational loop that you can look through. So that was the state of the art in Middle Ages. I made a quantum jump straight away to today's and future telescopes, and I'll just point some of them out. Take my glasses off. Here we have Hubble over there. Now, because it is a space telescope, it probably doesn't need such a large aperture. And for comparison, you have a tennis court and a basketball here, and these three over here are still under construction. I'll talk about this a lot more. Our Australian one isn't actually shown here. Maybe it's just one of many hundreds of telescopes that are used around the world. Now here we have two very interesting telescopes. Synoptic means that the word synoptic means that it's composed of many other elements. So if you have an 8 meters, it's like from here to there, a mirror, and you stand it up, it'll sag. And as it sags, it will damage distort the image. You should know that glass at room temperature is a liquid. I have personally seen windows of houses which were built during the Second World War, and they looked like that, with a bulge at the bottom. And during higher temperatures that we have in Australia, the glass actually melts a little bit. So an 8 meter mirror is about as much as solid glass can stand. However, this particular telescope consists of many tiny little triangular pieces which make up the total area, and they all synchronize together. And this is going to be used for making observations of the total universe. So it'll take a section of the sky of a certain width and go 360, and then do another one, until it's done the whole sky. And it takes thousands of galaxies into its picture. The Giant Magellan one is a piece of work. It has a central mirror here, and from that center of the mirror, they shoot out one laser beam, and I think there are others from elsewhere, to focus all the other mirrors out in infinity. So somewhere way past the moon, there will be a point where they all meet, and they decide that that's good enough for what you might call effective focus. Effective meaning good enough for the purpose. Each of these mirrors have what they call a optical active capability. What that means is that, I'll go back a little bit. Normally when you look at a star, you can see it blinking. And that is because of the effects of the atmosphere. And if you're trying to get an image or in long exposure, then all you get is just a blob. So what the technologists did, they introduced active optics, not like the ones you have in your glasses, but behind the mirror, there's a copper plate with tiny little hammers that move forward and backwards. And when a signal arrives, noise signal, it is instantly transmitted to the amplifiers, and a little rod comes up and changes the actual shape of the mirror. It happens in real time so fast that when you actually expose a star for a long time, you get a very sharp image. That was not available before. So each one of these mirrors here has this capability. And notice it has a total gathering space of 368 square meters. That's huge. Okay. Now, the Large Earth-based telescope, the VLT, this is positioned in the Atacama Desert in Chile. The reason they chose Atacama is because they get 1 or 2 millimeters of rain per year. Now, how is that for clear skies? And because it's high up in the mountains, they also do not suffer from the atmospheric and certainly now cloud aberrations. So these four telescopes can operate individually, and they can operate in unison, meaning focus on the same object and take different readings in different frequencies. Okay. Now, very soon we're going to run out of names. This one is called the Extremely Large Earth-based Telescope, the one on the right. It has an effective diameter of 40 meters, meaning that there are several 8-meter dishes within that. And in 2015, they were just grinding number 4. It takes about 1 or 2 years to do each mirror. And it is anticipated that this telescope will be ready to operate within a few years. The one on the left is being built in Hawaii, in Mauna Kea Mountain, and there's been a lot of controversy about this one. The local Hawaiian population claimed that it was on their sacred land, and here we are introducing technology, and there's going to be lots of trucks and people going back, and no doubt cafes and lots of noise, which is on their sacred land. But eventually, they made some kind of a deal, probably some currency change places, and it's under construction. Okay. Now, this is probably the largest earthbound telescope. As you can see, it's not a single telescope, and this one is of particular interest. All of them can be phased whichever way the observation goes, and they make different measurements, either in ultraviolet or in radio or in whatever. And then the data in what is known raw form, it's sort of like computer machine code that is gathered together, and there's absolute petabytes out of that data, and it's analyzed by computers, segregated, and finally given to analysts to make some kind of sense out of it. So this particular Event Horizon telescope was used to take the first photograph of a black hole, which is very far away. When the pictures finally emerged, this is of course false colors. If you happened to be there and look at it, all you would see is just white, the accretion disk of a black hole. But the amazing thing about black holes is that first of all, they have the accretion disk, which glows in different frequencies. We do not see them with our eyes, but there's lots of infrared and red, mainly infrared. And that light is seen from the side, and also the light that the black hole emits from behind is seen on top, as you see over here. Now, some black holes rotate, this one does, so it produced a very strange image, and they couldn't work it out. It's as if though you had say a globe of Earth, like you have in high schools, and you cut it in half, and the dome of it represents the black hole, and then you have the accretion disk, which would be a flat circular piece of paper, and then you took the one from the back and put it up at right angles. That's what you're looking at here, okay? Yeah, very interesting. Black holes are something of a pet hobby with me. I keep putting my glasses off and on because I can't see. All right. Now, when it comes to radio telescopy, the one on the left, which is located in Puerto Rico, known as the Arecibo, that was the largest telescope, radio telescope before, 300 meters from one side to the other. If you do remember the 007 movie, Brosnan, I think, fought the bad guy at the top over here. With a bit of luck and camera tricks, he won, and he dropped him down there. I don't think he recovered. And the telescope was severely damaged in storms, and the funding dried up, and they decided that the costs are not justified. So nobody owns it now. The amateurs think that there's lots of good value in this. All the structure is there. The electronics can be updated, and the sensors and everything, but there's no funding for it, so we don't know what's going to happen to it. The telescope on the right was built by the Chinese in 2016, known as the Heavenly Eye Telescope. It's 500 meters across. Now, think of a 100-meter dash, like you watch in Olympics. Well, 5 times as far. That's how big it is, okay? It is situated in a natural valley between mountains. And of course, getting to it was a real job. In China, roads are not known for their quality. You've probably seen some videos and movies of trucks going on roads which are about this big and a huge sheer drop on the side, and they're trying to pass each other, tricks like that. So access was very, very difficult. Most of it was lifted in by air. And when the telescope was actually built and ready to go, nobody wanted to work there because there were no schools, no cafes, no places to eat around there. And it was so far away that they had difficulty persuading some astronomers to actually work there. The one particular feature of this telescope is that it actually initiated the first kind of technology. It's made up of little triangles about this big, and each one of those can be individually positioned. So, for example, if they want to observe a star which is to the left upwards of this telescope, then the right side of the telescope can be tilted towards it and follow it. And the synchronization of the movement and the positioning of each tiny mirror is all controlled by a computer. Amazing, isn't it? So as soon as it started operating, it found some very distant galaxies. Very good. The Chinese are seriously investing some money in technology. Okay. Now, distributed array telescope. This is once again in the Atacama Desert. Astronomers found out very early in the piece that it's better to have a number of telescopes positioned and shaped in such a way that the resolving power follows that of radio antennas. So, for example, if I wanted to look at something where that light is, I would have a very narrow configuration. And if I wanted to look at larger picture, I would have an oval one, and so on. So it's possible to arrange all these telescopes. Each one of them weighs 100 tons, and they are 12 meters in diameter. So as you can see, they are not easily moved, but it can be done. And it's known as the millimeter array because they operate on a wavelength of 1 millimeter. It's like microwave in your kitchen. Okay. How are we doing for time? Am I in front, behind? Okay. I'll show you several images of these telescopes. The one on the left is an infrared telescope, and most of the South African telescopes, they got about 2/3 of the money. All of this was very highly politicized and managed from the money, and the politics were managed from Hague and a city in Europe, and we managed to get 1/3 of it. So Australia will be mainly looking at UV and ultraviolet. It overlaps a little bit. And South Africa is mainly going to concentrate on infrared. And there will be hundreds of them, both big one and small one. So as you can imagine, the cost of it is a matter of funding by several countries. So here's an example at the top left of some positioning of these dishes. And there's a different configuration over here. Here's some spider web-like antennas, and they all need to be focused and maintained. In Australia, in particular, they need to be operational at all times in the remote areas in temperatures which reach about 50 degrees centigrade, and lots of dust and storms and possibly animals or willful damage by passerbys. So each telescope each one of these units is connected by a grid of a local area network underground. And when it stops working or it has a problem, it sends a signal, and then the maintenance people come and replace it or fix it. Okay. Now, this one is more of a philosophical issue. How far can we see in the past? Here we are, Earth over here at the right edge, and there is the quantum fluctuation which slowly expanded and then gave rise to what we call Big Bang. Then there was hyperinflation, and then followed 100 million years of dark ages, and eventually, sorry, that happened here. Dark ages are here. This represents the first 380,000 years. After 380,000 years, the temperature cooled enough. The vacuum temperature of space cooled down to about 3,000 degrees centigrade, or physicists talk in terms of Kelvin, which is pretty close. So 3,000 degrees Kelvin was cool enough, meaning that electrons and protons had lost so much energy that they could not resist the attraction. Protons are being positively charged and electrons are negatively charged. They finally did not have enough energy to resist each other, so they stuck together. So when proton and electron merged, they made an element of helium. And from that moment on, we had chemistry. Now, you know very well that two, when joined, leave cheaper than two apart. There was excess energy, and that excess energy, mainly from the electrons, was radiated out in terms of the primordial photons. Today we call them cosmic microwave background radiation, or CMB for short. And if you're old enough like me, you may remember black and white television. If you tuned it to off station, you could see lots of white dots dancing around. 1% of those dots was cosmic wave microwave background radiation. That was discovered in 1964 by Wilson and company. And that radiation still exists everywhere in the universe, and in a way, limited by the speed of light, constitutes a limit to how far we can observe the universe. When I say universe, there are three different concepts of what we mean by universe. First of all, there's the observable universe, and that has a radius of 46 billion light years, meaning that light would need to travel from the center to the edge, which is known as an event horizon, for 46 billion years. So 93 or 94 billion years in diameter. This is the observable universe. Beyond that, we cannot see anything at all. But as the universe is expanding, the stars, which are now on the edge, cross that event horizon and they become invisible to us. The reason they become invisible, because light can only travel as fast as the light does, at speed of light, and it is originating, that light is originating at the event horizon, because once it passed the event horizon, it can't come back. So that constitutes the limit of our observation. And then beyond that is the rest of our universe. It is considered to be about 250 times larger than the observable universe. Now consider this. We might think, all right, we live on Earth, and let's say we are the only civilization in our observable universe, but there may be other patches in the larger universe who also have that observable universe limit. There could be several of them, but we cannot make contact with them. Not allowed. Physics doesn't allow it. So when you consider that, there's observable universe, and then there's the larger, our universe. And beyond that, there's multiverse. That is, of course, untestable at the moment, and it's pure speculation based on mathematical and computer models. So I just wanted to bring that to your attention, because we can only see a portion of the space within our observable universe, and beyond that, we can't. So here is a projection of how far we can actually see. There's the name there, observable universe. We can't get as far as that because this is what's known as dark ages. There's no light in there, but some light does come out in infrared or longer. So some telescopes can actually get to there. And in particular, James Webb can get very, very close. In fact, James Webb Telescope has started quite an upset, because we need to rethink how quickly the galaxies have formed and how fast after the Big Bang. The standard model of cosmology was very different before that. Now, you'll notice another dotted line running from us all the way to the Big Bang. This is the territory of the gravitational telescopes, and I'll talk about that in a moment. I just wanted to show you that as an orientation of scale. Okay, so let's talk about gravitational. Yeah, I've got the right one. Okay, I'll stand over here for a moment. What is a gravitational wave? Space-time, meaning the fabric of space, is made up of fields. They are, if you talk to cosmologists, you will get different numbers, between 17 to 24 different fields. And electromagnetic fields, electron field, a quark field, there's lepton field, there's Higgs field, you name it. So there's lots of them. And then there's gravitational field. Now, Einstein considered that gravity is not a force. Now, I drop a brick on my toe and I say, "Oh, Einstein, you were wrong about that. It hurts," right? But he concluded that gravitational field, which exists, is distorted by a mass, a body of mass or a body of energy. So a black hole, which is a body of energy, or body of mass, such as Earth or Sun or any other star, distorts that supposedly undulating near-flat space-time made up of all these fields. And Einstein said, right, if I have a body of mass, such as the Sun, then it'll distort that space-time like that. You've probably seen pictures of heavy balls on trampoline. That's a two-dimensional representation. You really should look at it from 3 dimensions, sort of like having a cardboard box being squished from every side. You need to think in 3D in this case. So in relativity, gravity is not a force. It is a distortion in the geometry of space-time. Okay? Whereas in quantum physics, they consider the carrier of the gravitational force, which is known as a graviton, has never been found, but it's mathematically sound to exist. And they consider that gravity is a force field. So we have 2 theories completely opposite to one another, not just in this issue, but many others, and we have nothing in between to merge them together. That magic something that is supposed to bring them together is known as quantum gravity. Quantum meaning at very, very small dimensions, like 10 to the minus 33. So when 2 black holes are about to merge, they create tremendous disturbance in that space-time, in the fields. But the wavelength, the amplitude of that wavelength is measured in squillionth of millimeter. I need you to process that. Despite the fact that there's such violence going on over there, if you imagine that you are standing near the pond with a long stick and you're doing that on the surface, you will see waves emanating in a spherical fashion. The amplitude of that wave will be dependent upon what force you're applying to the stick. Now, black holes are considered to be very forceful animals, and despite that, they produce very tiny amplitude, but extremely high frequency of reproduction. So these waves travel very, very closely one after another. Now, this is how, these, by the way, are those 2 images there are really diagrams, an artistic impression of a black hole and either two neutron stars or 2 black holes merging together. And when a wave travels, say it meets Earth, first it squashes it this way, then relaxes it, then it squashes it sideways. It's like having a rubber ball. You squash it that way, relax it, and then you squash it that way, and then it passes. And everything's hunky-dory after that. So that's exactly what's depicted over here. If you move from left to right, gravitational wave hits it. Well, I said it just the opposite way. Yeah, at first it squashes it in vertical set. Sorry about that. and then relaxes, and horizontally, and so on. So the field, the gravitational field of these waves, as it were, moves like a tube, like this. And it actually alters the shape of everything in its path. Every star, to a microscopic amount of millimeters. You wouldn't even know that it's gone past you. However, the gravitational detectors are sensitive enough to see that. And I'll show you some diagrams how this is done. Okay. The box at the bottom left is the centerpiece of the Light Interferometer Gravitational Wave Observatory, known as LIGO. And this box is what you see at the intersection of this diagram here. So a laser gun produces a beam of light, which is bounced off a two-way mirror and goes into one tube. That tube is 4 kilometers long, and it's supported, and it's terminated by a mirror which is suspended on extremely sensitive cushioning. If a fly went past it, it wouldn't even move. It's so sensitive, so well protected. And so the light goes up there, bounces back, it's focused here, goes back, and is refocused again, because even laser light, when you put it long distance, it will disperse a little bit. See, over here, the pointer is very concentrated, whereas if I put it over there, it's already bigger. So if you have a longer distance, they do tend to diverge a little bit. Okay, so that's one path. The other half also goes through, it's refocused, bounces off the other mirror. And when they arrive together, they are so synchronized that they arrive together, and there is no difference in phase between them, then you get no signal. This is what happens when the black holes are circling each other. But when they actually come to contact, this happens very quickly, probably within 1/3, and certainly under 1/2 of 1 second. They actually capture the sound of it. It sounds like a chirp. It goes like this. That's what merging black holes sound like. Of course, they are much lower, 40 octaves below, so it's all speeded up so we can actually hear it. Yeah. And it so happened that when the first LIGO observatory was built in 2015, within days, there was a collision of 2 black holes, one weighing in at 29 and another one at 35 solar masses. And that was very fortunate. So it verified the technology. Einstein predicted that, and it took 100 years to build the technology to actually make it good. So much for all the objections to wild theories that have now experiential testability. It took 100 years, but we did it. The same thing happened to Higgs field. Way back in 1964, Peter Higgs predicted there must be a field with which elementary quantum particles interact and acquire mass. And the paper was rejected. That's baloney. So he rewrote the paper, and on the margin it says, and by the way, there should be a particle associated with that field called Higgs boson. Well, it was found in 2012. So there you go. Here we have, at the top, we have 2 images, computer simulations of what happens in terms of disturbance and effect on space-time of the 2 bodies that are about to merge. And there is one of the telescopes, and this particular telescope, known as LISA, which will be operational in the near future, that will observe, it'll circle in certain distance from Earth and change position, probably on a 24-hour sync with Earth, and periodically test positions of object of interest. So that's really interesting. I should mention that collision between black holes in our galaxy happened once in several hundred years. But because there are squillions of galaxies out there, they happen all the time now. In fact, they happen so often now, we can't process the data fast enough, because each run of the LIGO observatory produces terabytes of information, which needs to be correlated and analyzed. And two others are being built as well. Okay, let's talk about Space Telescope. You're probably most familiar with the Hubble. Hubble has been decommissioned now, but it runs so well that it's still being used. It has been replaced with the James Webb Telescope. In addition, we have the Chandra, which is a X-ray. That's a very small telescope, and Spitzer and Compton. They are aging very, very quickly, and I think James Webb will probably replace all of them. What happens to the old telescopes? They just come down to Earth and crash and burn up. Okay, let's talk about James Webb. This is probably technically the most audacious and successful experiment in astronomy. So many things could have gone wrong and none did, right? Imagine, this is the size of each mirror, like this, like a honeycomb. Now, all of this is folded inside the rocket. And as the last stage of the rocket finishes up, it opens up the door, the thing flies out, and it unfolds very slowly as it travels. It has a number of protective shields, curtains as it were, to stop sunlight from getting to the electronics, because the temperature outside is several degrees above zero, 2.7 degrees above absolute zero, okay? And that's the temperature that the cryogenics and the amplifiers need to work. Now, the electronics themselves cause a lot of heat. You might not think that tiny little amplifiers and chips produce a lot of heat, but compared to that temperature, it's like walking into the middle of the sun. So that's been extremely well done. It was launched in December 2021, and it has a collective gathering space of 24 and a bit meters. Yeah, it's named after James Webb, who was the director of NASA for many years. There's been some attempt to change the name of it, but the protesters have won the day. Here in the top image, we have it under construction, and then transported, unfolded, and begun operations. Now, a little bit about geometry of space and physics for you. Here on the left-hand side, we have Earth, and somewhere out there, past the building, we have the sun. In the meantime, we have the moon here, and somewhere here, because of the relative size and proximity, as opposed to relative size of the sun and its further distance, the gravity of each cancel out. This is what's known as a Lagrangian point. And it is so in the entire orbit, to make it work. If the James Webb is over here, then it'll have an orbit like that. A mathematician by name of Lagrange, a French mathematician, worked it out. So that's where the James Webb sits. But because of different instabilities and radiation, it will drift a little bit because space is not empty. So it has little motors and sensors to keep itself in that position. It automatically adjusts. That's the physics of it. And there it is. I copied that from a magazine, hence the curvature there. This is the orbit. As you can see, it's upside down. The shields over here are to protect it from the radiation of the sun. Even though it's so far away, the impact of the sun rays is unacceptable. So there's the sun over here in the bottom right-hand corner, and it can heat it up over time up to 85 degrees C, whereas the outside of it needs to be kept at minus 233. So you can imagine what sort of technical difficulties there are in all that. Well, as soon as it was launched and became operational, it caused a major upset amongst cosmologists. It discovered stars which were older than the universe. Well, how can that be? That means something doesn't add up. Either we got the age of the universe wrong, or we have the speed of formation of galaxies much earlier, and hence formation of stars. The star that it found was 13 billion years old, and the universe is only 13.8 billion years old. Wow, you know? So there's much work. To this day, the actual process of how galaxies are formed and what was the causation for that, what was the actual fluency of the process, has not ever been established. The general, what is known as a standard model of cosmology, says that during the Big Bang, the energy was fluctuating all the time, quantum fluctuating. And these fluctuations have magnified into movement and coalescence of the gas clouds. The gas clouds, the initial gas clouds, were larger, many times larger than our galaxy here. And when there's some matter over here causing gravitational field, more matter gets attracted to it, sort of like rich gets richer, like little rivulets find other rivulets and they make a river. And eventually, one side of it will have more charge or more mass than the other, and the whole thing starts rotating. Once a galaxy cloud, not even a galaxy yet, once the cloud starts rotating, it starts emitting radio frequency energy and losing speed. And as it does that, it flattens. Hence, most galaxies are flat disks, almost flat disks. Some are barred and some are, but they go through a progression of irregular size to one through the arms. They develop a bulge. Our own galaxy has a bulge in the center, and some don't have a bulge. And eventually they all finish up to be elliptical blobs. But that's by the side, yeah. So that's James Webb. Now, it is considered that James Webb will go way past, and it did. This diagram is older. You can see 10 years ago, we still thought that the universe was 13.7 years old, so that's how old the slide is. I deliberately used that. Yeah, Hubble can see about this far back, and James Webb sees almost up to the beginning of, up to the end of the dark ages, where first galaxies and stars have formed. There it is there, first stars and first galaxies. But 400,000 years. Okay. All right, so what's next? A lady by name of Nancy Grace Roman has been the mother of the Hubble, and in her honor, a new telescope is being named the NGR telescope, and is going to be launched very, very soon. And this is mainly to look for exoplanets and the effect of expansion of the universe. You've probably heard ad nausea that the universe is expanding, but nobody really knows why is it expanding. You know, the initial force, the initial impetus of the hyperinflation, if that ever happened, it makes sense, but that doesn't mean it's true. If that hyperinflation happened, that energy has dissipated itself and converted into radiation and later into matter. And the universe just slowly started expanding. But 9 billion years later, meaning 5 billion years ago, it started accelerating its expansion, right? And that is a completely new phenomenon. And it's known as the effect of the dark energy. It's dark because we know nothing about it. The popular theory, unproven, is that vacuum is full of fluctuations in energy. Particles pop in and out, and they are positively and negatively charged. They pop out in pairs, they annihilate each other, they go back into radiation and back into the field. But during that time that they are, so to speak, airborne or vacuum-borne, which is 1/20 zeros of a second or thereabouts, they repel each other because they're made of the stuff that repels each other. That's part of quantum physics, which is another lecture. They actually repel each other. And for that tiny period of time, 1/20 zeros of a second, they repel each other. But because it happens all the time, like there's a foam of this stuff all the time, the cumulative effect is expansion of space. And that apparently is what we call dark energy and what Einstein called the cosmological constant. So this telescope is going to look for that, for the effects of that. Now, this is not a telescope, it's an International Space Station, and that is not used so much for astronomical observations, but rather on the effect of space on biology. It is a confirmed fact that if people live longer in zero gravity, then their physical faculties stop working. Blood doesn't circulate very well, bones don't form, and there are all kinds of things. Our physicality grew in Earth, developed in Earth gravity. And our senses and our psyche and our reasoning and our logic developed in that manner. So people think that it's just possible that there's some kind of limit to our ability to explain the universe. But that's philosophy. Yeah. Sorry, did you have a hand raised there? Sorry. Okay. So the station here is built to measure effect mainly of humans in space, growing their food, surviving on that food, what metabolism changes they actually experience, what's it like to live in zero gravity all the time and lose all your muscles, you know? And there are so many biological factors that it's really scary. Plus, of course, radiation. Yeah. So that's an experimental station. I'm nearly at the end. So in summary, we have started off with optical telescopes, small ones, of course, both reflective and reflective. And then Galileo built his first telescope, and he got into trouble with that. Newton followed up on that, and that's what most of telescopes are now based on. And most optical telescopes work and are built for working in specific range of frequencies. The square kilometer array operates in the infrared, and so does the James Webb. The light interferometry gravitational wave observatory, quite a mouthful, LIGO telescopes are now operational, and there will be 3 or more of them built shortly. And they are very large computer networks, including the internet, used to distribute the information. You can actually contact NASA and offer your laptop to be on the net during the night, and they will pay you for it. Yeah. So this concludes the formal part of my talk, but I want to show you very quickly some sample images of supernovas, which are caused by collapsing stars. There's no music associated with that. Picture tools, slideshow. Yeah, here we are. You've probably seen many of these images in magazines. Most of these are from NASA, and no doubt some of you have photographed. This is known as the Eye of God, or the planetary nebula. Yeah. There's about 20 odd of them. The colors are totally false. Number of different observations are made, and then the different frequencies represent different colors. So if you happen to be near something like that, you would see just a white flash, nothing else. This is a neutron star. That's an interesting one. I haven't seen anything like that before. This is the one that the Chinese have, the Crab Nebula, recorded. These are what's known as stellar supernova. Supernova stands for explosion of a star, whereas nova has 2 different meanings. One of which is a new star. It's a Latin word. That's the end of that. And another definition of nova is I need to describe it. Imagine that you have 2 stars circling each other in a binary formation, and most stars are born in groups of several in a cloud, and then they drift away because they repel each other. But some of them are in such ratios of mass and proximity that they start circling each other around a common center of mass, and these are the binary ones. Eventually, the fuel will expire, and one of them collapses into, if they are small enough, they collapse into a white dwarf, just like our sun will. And that white dwarf now has a very strong gravitational and magnetic field and starts sucking off dust from the other one. Now, you would think, logically speaking, that if it puts on enough weight, then it'll collapse into the next stage, into a neutron star. But at about 99.9% of its weight, where it should collapse into a neutron star, according to all the maths, it doesn't. It just fizzes out, sort of like a phosphor, like lighting a match. And that explosion is called supernova 1A. one of the major attractions about supernova 1A, that it has virtually constant luminosity. And once you measure something that is close and you know how luminous it is, you know the distance, then by measuring luminosity of a distant star, you can tell how far it is. And the measurement of the receding supernova 1As in 1998 helped two separate teams, American and one Australian, to establish that the universe is actually expanding. That was put to bed, and they received a Nobel Prize for that. And on that note, I shall quit.
Whoa. Are we there? Yeah? Can't quit yet.
Ran out of time?
No, we're good for time. We have a question online.
Okay.
Are you a visual astronomer? Do you
No.
look through have you ever looked through telescopes?
Yes, once with ISV.
Okay, so the question is then, what is the best observational telescope you have looked through and what made you dig it?
I couldn't tell you what observational telescope I looked through because there was a long line of people in a cold wind, and I finally got to it. I looked at Jupiter. It looked like something, and I went back.
So it left an impression at least.
Yes. Yes.
All right, so what's your favorite non-visual telescope?
It would have to be LIGO.
LIGO?
Yeah.
Why?
Yeah, because it goes further and it delivers enormous amount of information.
Any questions in the crowd for Bruno?
No?
No, you've bamboozled. Oh, we've got one. I thought we'd bamboozled the crowd.
Okay. I'll come over here.
Nice
away
shot
from,
of Cartwheel Galaxy in
I'm
there too.
away from that light.
Hello.
Yeah.
It's not really about telescopes. I just have I'm new to this, but can I ask, like, what happens if you enter a black hole and question like that? Or
If you happen to enter a black hole, okay, there's a principle of complementarity, and it says this: if you happen to be an observer outside of the black hole and you watch your mate jump out of in a suit and go towards the black hole, the observer on the ship will see you approaching the black hole, slowing down. At first quickly, and then slower and slower and slower. He'll never go in. The astronaut will never go in. It just becomes redder and then just disperses. On the other hand, if you were the guy that fell in, you wouldn't even know when you went through the event horizon, the sort of an invisible shell where black hole ends, so to speak. You wouldn't even know. But as you were going towards the center of black hole, you would notice very strange effects. Let's say that you jumped in feet first. You suddenly find your legs being extended like on a rack, and the whole lot of you become spaghettified. And before very long, there'd be nothing left of you, just quantum particles. So, and you couldn't even say, Mum, I've been there, because no signal can come out.
thank you.
Right.
Just if I may ask a quick,
Yeah, go on.
how do they get the space station and how big is it? How do they get it out there and how big is it?
That's a technical question. I think they've built it in bits. Number of rockets, deposited bits, structural pieces. It's sort of like watching a building go up. You know, you have the ironworks, and then you have the columns for the elevators and so on, and then they put skin on it and glass and all that. I think it was that kind of thing, but I'm not sure.
Do we have any other questions? Oh, we do have another question.
Yeah.
For black holes as well, what's happening when you go into black hole? What's at the other end? At the other end of
That's an interesting question.
Getting deep, Bruno.
Yeah, it's getting deeper. Okay. The common wisdom until recently was that once you fall into a black hole, eventually you hit the singularity, and your entire body is ripped apart, the stuff that you've made of is not even matter anymore. It becomes energetic particle. You become part of the singularity energetic field. And the singularity is not a point. It's a sort of an area ill-defined which changes shapes at an incredible speed. That's one theory. The other theory says that there is no volume in the black hole. There is no center. All its energy is outside in the gravitational field. That's Susskind theory. Rovelli, another scientist, says this is what happens. A star uses up its fuel and its core collapses under its own gravity into a black hole, okay? And until recently, we thought that's the way it is. A black hole is a black hole is a black hole forever. It does evaporate a little bit. If it stops eating, it loses weight because of Hawking radiation and all that. And over 100 trillion years, it'll probably just pop. Fine. But along comes Rovelli and says, no, something different happens. That core doesn't just stop shrinking. It shrinks and shrinks and shrinks until it can shrink no more. It reaches what is known as Planck's scale. It becomes a quantum star. Planck's scale is 1/99 zeros over centimeter cube, if you can imagine that. Okay, it's about this big. So space and energy cannot be compressed beyond that. Once the compression reaches that level, it bounces back and it starts growing. It grows and grows and grows until it reaches its original size. And because it went through a phase change, it reversed itself. It becomes a white hole. Now, black hole, stuff goes in, nothing comes out. White hole, nothing can come in, things only go out. That has never been tested yet, although some astronomers think that they might have found one that could possibly qualify. So it's work in progress in early days.
Do we have any other questions for Bruno? No, well, Bruno,
Well done.
Thank you very much for another wonderful talk.
Okay, thank you. Thank you.
I think based on the questions, we're going to have to get you back later in the year to talk about
Okay,
quantum.
we'll talk about that.
We shall talk about
Can
that.
I get my gear?
You can. It's been lowered down there. Now, while Bruno moves his stuff off and Bill gets his stuff going, I'm going to hand over to Ken Lamarcand, who's going to have a chat about the Lone Telescope program. Are you going to do it?
Thank you, Matt. No, not this time, but I'll have to come up with another one, won't I? Yeah. My name's Ken Lamarcand. I run the Lone Telescope program. So just up here to say, in about 3.5 weeks' time, there's another set of Lone telescopes to go out. Only a few have been booked, so there's plenty available. So jump online. I got up here last time and there was 10 left and they were all gone the next day. So they're available. Telescope sits about this high. I'm going to put a new picture up on the Lone Telescope page because someone turned up with a little Subaru sports car and we managed to squeeze the telescope into the back seat with a few millimetres to spare. And then we waved furiously goodbye. I'm hoping they got it out of the car when they got there. So I'm going to put a few more pictures up just to let people know how big they are. But it's an 8-inch Dobsonian telescope. There's two different brands, a Saxon and a Bintel. They're very much exactly the same when you look through them. If you're trying to decide which one, look at what accessories comes with them. One might be more suitable for you. They're both trying to compete with each other, so they're both a little bit different. Now I'm going to go out on a limb here. I could get myself in trouble, but we are after bits and bobs to keep the Lone Telescope scheme going. Now, we could go out and buy bits and bobs, but some of these things are really hard to get. And the bit I'm scared about is everyone is going to flood me with a whole lot of junk. That's the bit I'm worried about. So we're after bits and bobs, unused spare parts that you might have. Some of the stuff you may think is junk is absolute gold to us. So we're looking for caps for eyepieces, for finder scopes, that little rubber O-ring. So if you have a broken finder scope and you think, I'll just throw that out, send me a picture or a couple of pictures and write a little sentence, what you think it is. It could be the plugs that go into the tubes. So when you have your telescope, the little 1 1/4 inch and 2 inch plugs that go in there, the little screws that you tighten up your eyepieces with. If you have a broken Telrad, it doesn't work, something's broken, it's full of little pieces that we can use to repair things and keep them going. And we're also after a few simple Plossl eyepieces. So we're after like a low power 2 inch, so something in the 25 to 35 millimetre. 1 1/4 inch eyepieces for medium power, that'd be 15 to 20 mil, and a high power in the 5 to 10 mil. So if you've got some of this stuff, you've had it for years, I can't bring myself to throw it out, it's valuable, but I'm not using it, well, we might be able to find a home for them. And something like a Barlow lens, 1 1/4 inch in a 2 to 3 power range. These are little bits of gold for us. And all those little grub screws, the adjustment screws out of mirror cells, all those little things can make a big difference to keeping our program going, because things break, they wear out, they get lost or in the dark, or they get left behind and no one's going to drive 100 kilometres to go get into a lens cap. So if you've got something, send me a photo, send me a little description. My email address is loanscopes@asv.org.au. I'll say it one more time, loanscopes@asv.org.au. And when I've got the right words, I haven't got the right words yet, I'll send you something, Mark, to send out. Yep. Thank you.
I may have a Barlow for you. 3 times. All right, without any further ado, it is time for Bill Stent, the telescope gent, and here's what's in the sky.
Hey, am I talking? Oh, yes. Hello. Greetings, Earth creatures. Can we have these off? Oh, I have to normally turn these in. Oh, no, I don't. I'm very ethereal today. Okay. Without any ado at all, what's in the sky for late January, early February? This is becoming routine for me now. So if we go, there we go. Now, as normal, we're on the lands of the Bunurong and the Wurundjeri Woi-wurrung people of the Kulin Nation. I'm going to talk about general conditions at this time of year, which is warm. I'll do a quick review of how to read the sky maps. I haven't done this for a year or so, so I thought I'd just give it a quick refresher. Then I'm going to get into the normal stuff. Where's the moon? Where the planets, orientation, stars, constellations, suggested targets for tonight or this coming month, visual and photographic, and then I'm going to talk a little bit about the early risers, just to get ahead of myself. The early risers are it's a fairly boring time for the early risers at this stage. Then I'll finish off by things to look out for this month. Okay, does this sound all right? It sounds really awful to me. Yeah. It's okay? All right, okay. So general conditions at this time of year. First of all, welcome people to 2025. I've been writing 2024 and all of my dates, so it'll take me a month or so to get to catch up. Summer. we had a bit of we've only had one smoke haze event this so far this year. Actually, it was probably late last year. It was the one from Birdwood. The smoke haze makes for lovely sunsets, but it really stuffs up your seeing. So yeah, that's just what happens at this time of year. Sunset is very late still. It's about 8:45. Dark about 9:20. Astronomical darkness is sort of after 10 p.m. Next month, that's going to wind back to 8:25 p.m. So we're getting a little bit more over the next month as we're getting closer towards the equinox. Sunrise, the same sort of thing. The sunrise is about 6:10 a.m. and next month it's going to be about 6:45. So we actually get quite a lot more darkness in the next month. Quick little bit for young astronomers. I like to throw a bit in. Orion and Scorpius are two of our main signpost constellations, which I'll talk about shortly. Why is it that we say that they play hide and seek, or they hunt each other, or chase each other around the sky? It's part of the astronomical sort of lore. Anyway, so that's something for the kids to think about. Right, these maps are. Most of us are probably familiar with them, but new beginners do often have a lot of trouble with maps like this. I normally show the whole sky because that's the way it comes out of the computer. Now the zenith is up the middle there, that guy there. That's the bit directly above your head. It's horribly confusing unless you're lying with your feet pointing south and you're looking straight up. So if you're standing up and facing south, north is behind you. You can't see it, so there's utterly no point in even talking about this part here. The zenith is above you, so what we normally do is zoom into just that area there. And so we're going to change the perspective a little bit. If you can, who hasn't got one of those phones that you can wobble around and it shows you what you're looking at? But if you can, get your phone to get into that mode and hold it in front of you. So you face south and zoom in so the zenith is near the top. And that's what you're closer to you actually seeing. And I've got one of those here. So I've just zoomed in. And so there's the zenith at the top and we're facing south. So this is us looking south. So you can see the Southern Cross a bit to the left of right in front of you. And Venus, just at the moment, is way off to your right because it's setting in the west. Now, if you turn to the west now, that's moving to your right, you kind of grab the map and you roll it so that west becomes the bottom and it looks like this. So now Venus is in front of you there and the cross is behind your left shoulder, so it's sort of like over there. So keep on turning and you go the next thing where north is the top, is in front of you. The zenith is still at the top. And then you can see Orion. Where's Orion? There it is. And you can see that he starts going from the east and he sort of goes off towards the west. So keep on turning to the east and now you get to see Mars, which is at the moment rising right. Oops, hang on. I think I might have pressed the wrong button there. There you go. So Mars is rising, and you can see the cross off on your right, which is nearly south. So this is how you use those maps. Now, if I just go back, I don't know if I can go back. Boop. So if we zoom out, we get all of that information on the one page. So when you're facing south, you're only interested in. Oops, I'm very good at this, aren't I? Had lots of practice. So when you're looking south, you only look at that bit. When you're looking west, you only look at that bit there. When you're looking north, you only look at that bit there, but you turn the map upside down. Otherwise, you could stand on your head, I suppose. So that's the way you use these maps. Right. And, oh, there you go. So, yeah, unless you're, like I said, you're with your feet pointing south and you're looking straight up. Okay. Where are the moon? Where is the moon? Is Kelly here today? No. Oh, hello, Kelly in cyberspace. This is a shot taken by Kelly of a maxi and a mini moon, so you can tell the difference in size. I believe that's a C-star image, so don't say I never show C-star images. Right, full moon is on Tuesday the 14th, next week. It's well into the north on Tuesday, the 14th, which means it's going to rise and it's going to be low in the sky. It's going to be low in the sky for another week. It's about the middle of its distance, so it's a meh moon. It's sort of neither that size nor that size. It's in the middle somewhere, but you can hardly tell the difference. It rises at sunset, sets at sunrise, which means that it's poor viewing because the light is dead on to us. We don't actually see any features of the moon, so looking at the moon during the full moon is not actually all that amazing. And obviously you can view it all night. And the following as a waning gibbous. Last quarter is on Wednesday the 22nd, it's a week later. Now it's crossed to the south by this stage, so it's going to be getting high in the sky again. So last quarter is going to be a bit irritating for the astrophotographers. It's about as far away as it gets, so it's a mini moon, or mini last quarter, I suppose. It rises at midnight and sets over the following week as a waning crescent. It's going to get thinner and harder to see as it approaches the sun, as always, and you'll view it in the morning and later this week in the early afternoon. So the new moon, this is the astrophotography's time, it's on at the end of January. It's opposite, it's with the sun, so it rises at sunrise and sets at sunset. It turns into a waxing crescent, very thin after the next few days after that, and you'll be able to see it. It's just a few minutes after sunset. It'll be very close to the sun and hard to see. First quarter, 5th of February, rises at noon, sets at midnight, which is the best time for viewing for if you've got a star party going. It's a waxing gibbous for the week after that. It's going to be back in the north, which means it's going to be low in the sky again for the next 10 days or so. And all these numbers and phases are all that little graph I was showing last year. Obviously, the next full moon is a week after that, and that's just in time for the next meeting. Okay, moving to the planets. Let's see. Mercury, it's a morning object. It's very much in the twilight. It's going to be very, very hard to see. So it rises about 4:45. It's kind of difficult. Venus, it's still an evening object. It sets fairly late. Greatest elongation is on the 10th, which is in a few days from now. So it's good evening viewing right now. I think it's probably still behind buildings from the lower observatory. Mars it rises at about 9:45. It's coming into opposition shortly. It's only a couple of weeks away now, so it's the best time to observe Mars. Elon Musk needs to know it's a great opportunity to actually go there. Wouldn't that be nice? Jupiter sets at about 3:45. It's still good evening viewing. It's at just after dinner time, after sunset. It's more or less crossing the meridian, so it's kind of in the north, about 45 degrees upwards. It's very easy to find. Remember to check the phenomena tables in the ASV yearbook for shadow transits, red spot viewing, etc., etc. If you don't know how to do that, ask me or Colin or any one of the demonstrators. The monthly pages, that's the ones sort of that show all the monthly stuff. They also show the positions of the moon each night. So you'll be able to see those little squiggly diagrams down the side of the page. Saturn it's past its prime, I'm afraid. But it sets just before midnight. It's still following Venus, fairly close to Venus at the moment. The rings are getting very close now. They will actually close after conjunction, which means that they'll close when it's a morning object. That's the 23rd of March. It's still a couple of months away. I'm kind of looking forward to Saturn completely with no clothes on. That's Saturn will be naked, not me. Uranus, speaking of Uranus, sets at about 2:30. It's good evening viewing. You do need to be able to find it. It's still ahead of Jupiter. It's actually not very far from the Pleiades. Neptune, it's in a bit of a conjunction with Venus and Saturn. It's again a bit hard to find. You need an SCT, and it's kind of greeny blue colour. It sets just after midnight, about half an hour after Saturn. And Pluto is very close to the sun now. It's kind of near conjunction, so it's going to be hard to see until late February. Okay. Now, we have been hearing quite a lot about a planetary alignment. There is no planetary alignment. It is complete alternative facts. However, there are going to be 6 planets in the same sky around about now towards the like end of January, maybe early February. So the 6 planets are Venus, and then right next to it is Saturn, and if you can find it, Neptune, not very far away. Then there's a gap, and there's Uranus, and Jupiter's not very far from Uranus, and like I said, it's on the meridian, and Mars is just rising. So we've got 6 planets in the evening sky about now towards the end of January, which makes morning viewers very, very bored. So that's, I think, what they call that. They call it in the media as a planetary procession or parade or something like that. But it's certainly not the alignment that the astrologers are talking about. Remember also the date is not super critical. We're not talking, it's got to be the 28th of January. It's, it's a week here and there. It's not going to make much difference. Okay, so let's get orientated to the evening stars. This is at 10 p.m. facing south. Although remember, you stand on your head, you can see the north. The Southern Cross, one of our little signpost constellations, is down there. It's getting towards 8 o'clock, which means it's starting to rise. It's been dragging on the ground for the last couple of months, but it's starting to rise again. Just get rid of that. There you go. Now Orion is approaching a meridian. Maybe I'm just getting old, but these things are happening faster every year. Obviously Scorpius is not there. The orientation stars, we've got, back to the clock, we've got Canopus, which leads the cross around the pole. So we've got, there's the cross and there's Canopus, and Achernar is the next one. It's opposite the cross. So that's a sort of a way of finding out which one's Canopus and which one's Achernar. Then you've got Fomalhaut, which is sort of obvious, but it's kind of dwarfed by Venus and Saturn, but actually less Saturn. And Sirius, it's bright, 45 degrees in the east. It's very obvious. Aldebaran, it's about to pass the meridian, but probably the easiest way of finding Aldebaran is by finding Jupiter first. Procyon is between Orion and the east-northeast horizon. It's not normally a star that I use as an orientation, but it's kind of there. For planets, like I said, we've got Mars, we've got Jupiter, we've got Saturn, and we've got Venus. Okay. So moving to the visual targets. This is for the visual astronomers because they get the best time. Okay, we've got Saturn. These are what I'd start with. Saturn. Actually, if you can't see Venus, you probably can't see Saturn. I've left out Venus because it's dull as dishwater. But Saturn's there. Saturn's still pretty good. There's 47 Tuc at this time of year. It's sort of a little bit past its best, but it's not too bad. And that's circumpolar, so it doesn't really matter. P. Eridani, cat's eyes. It's a yellow double, really, really easy to find. It's only 1 degree off Achernar, slightly to the north from Achernar. You can actually see it in your finder scope, so it's a really good one to find. Theta Eridani is less easy to see, but it's another good double. It's almost straight up, so it's what I call a donut warning because it's in that area where it's a bit hard for a lot of telescopes to see if your dob can't point straight up and stuff. Mark calls it a dob hole. There's a Tarantula Nebula, which is good pretty much all the year round, but it's pretty much at its best now. I've been using it as a test image. Pleiades is very obvious. It's the best time of the year for the Pleiades right now for late evening. It's on the meridian, so I got a shot of it last night. Gamma Arietis, Mesatham, it's kind of got squashed by the moon tonight, but of course the moon's going to move off that way. So, no, sorry. Yeah, that's right. So it's that's a nice double. At this time of year, I'm going to have to cough again, sorry. M42, Great Nebula in Orion, is everybody's favourite visual nebula. It's very, very bright and very obvious. It's the middle star, if you call it a star, in the sword of Orion. not the belt, it's the sword. Jupiter is still there, obviously. Please look at Jupiter, it's really cool. Pollux, now Pollux is just rising now, it's near Mars, and Pollux is a double, and I didn't know that until relatively recently, and it's actually really cool. So it's easy to find too because it's near Castor. Castor and Pollux are the two twins in Gemini. Obviously Mars, you probably want to wait until later in the evening when it's closer to the meridian. Because it's coming into opposition, you will probably be able to resolve it quite well as a disk. It's getting quite large. So yeah, keep an eye out for that. It's well worth watching. I think this is the last one. Southern Albireo is my favorite double. It's a really, really pretty colored double. There's one blue one and one yellow one. So that's very pretty. And it's not too difficult to find. It's not far from Sirius. Okay, so they're the visual targets. Let's move to the photographic stuff for the true geeks. 10 p.m. facing south again. Okay, so we've got NGC 1365, donut warning. Now, this is one of Yuri's photographs from quite a while ago. I've actually repeated a lot of this because I didn't have a lot of time to do a lot of preparation for this talk, so sorry about that. Large Magellanic Cloud and the Tarantula Nebula. That's one of the remote domes photographs. We've got the Pleiades, which no show is complete without an Andy Pang photograph. I got a shot of the Pleiades last night, and it was just nothing like that. The Pleiades is a super big cluster. I don't know what focal length he was using, probably a camera lens or maybe a Red Cat or something like that. It's very short because that is enormous. I can't get that into a field with the remote dome, which has got an Esprit 100 and a 268. So that's about that big. It's not quite big enough to show the Pleiades. 47 Tuck and the southern, the Small Magellanic Cloud. Thank you, Jeff Healy. So that's another fairly wide one. There's another Eddie Pang photograph of the Crab Nebula. I don't think I could possibly take a shot like that. That's awesome. Rosette Nebula, that's one of mine, I think, in hydrogen alpha. So that's also really big. That's actually two shots stuck together. Yeah, that was the one I got a couple of nights ago. It wasn't a good night. Elon was not kind that night. That's just a sub. It's the reason why it's not so bright. Carina Nebula. Some idiot took that using not a mobile phone. Notice. So congratulations, Mark. But one thing, dude, you can't read it. It says, dude, you need a coma corrector. That star and that star are shit. No, it's a coma problem. Yeah. Southern Pleiades is becoming, it's down there. That's coming into view again, and that's very pretty. My photograph probably doesn't do it justice, but if you're a visual astronomer, have a look at the Southern Pleiades. They are pretty as, and it's the bottom end of the Diamond Cross, which is that one. That one. So that's pretty much all I've got for this. For the early risers, there's not a lot going on. As you can see, the Southern Cross is rising. It's coming up towards the meridian. It's about 11 o'clock. Get rid of that. Orion is now setting, and this is for the young astronomers. The Orion is setting, and Scorpius is rising. They're chasing each other around the sky. Planets. Buckle yourself in because there's not an awful lot going on. Jupiter has gone. Mercury is just rising. That's hardly visible. Mars is kind of the only one that's really any good at looking at. So sorry, guys who have kids and dogs, you're not going to see much. Okay, final notes. Some random observations. First of all, Venus's greatest elongation is on the 10th, which means it's going to be sort of the maximum distance from the sun. Mars, obviously, it's Mars time of the year. 13th of January is its closest approach, please. And 16th of January is the opposition. They're very close to each other. Late January, the sky full of planets, remember. The end of January, Uranus is stationary, starting retrograde, which means it's going to chuck it in reverse and go backwards. The 5th of February, Jupiter is stationary, but that's when retrograde ends. So it stops going backwards and starts going forwards. Early February, please start watching T Corona Borealis again. It has not yet gone off. I've taken so many photographs of it, and it's probably going to be visible again. So don't tell me it's got about a week before it goes. So anyway, we'll see what happens, and I'll see if I can get some more photographs. The light curve has been wobbling around all over the place. Now, this is a quick additional note about astrology and astrology web pages. Remember, please, people, astrology, be nice. Astrology has been a precursor to astronomy and a modern scientific methodology. Historical astrologers, yes, Kepler and Brahe, and also Copernicus, I believe, studied the motion of the planets very, very carefully and accurately, and that is what gave rise to modern astronomy. So because they were very interested in what the planets may or may not be doing to you, they observed them very, very carefully. And that is where we got our data, or should I say that's where Kepler got his data. So a modern astrologer, some agony aunt in the newspaper, will make a statement such as, Jupiter is entering retrograde on this date and therefore you will feel anxious. From that, you read, Jupiter is entering retrograde on this date. And you just ignore the rest of that. The factual part of that sentence is entirely valid. And that's the reason why I get so much of my information from astrology pages. So there you go. All right. Thank you. What, you are astrologers? I mean, both. T Coronae Borealis. The blaze star, it's called. Yeah. Okay, it's up in the mornings. It's a morning object, and it's from the remote dome at LMDSS or anywhere on the astrofield of the LMDSS. It's still in the stars. It's still in the stars. It's still in the.
It is still in the stars.
Yeah,
Yes.
still in the trees, right? And it goes up. It's not from here. It's not very not very high. So I think it's a little bit like trying to photograph Andromeda. It's sort of like just out of the trees and it skirts over the trees.
So what you're saying is go up on the visual field.
Well, yeah, that's right. But I can't move the dome.
Well, we could.
No.
Give it a shot. All right, thank you, Bill, for another wonderful presentation on what's in the sky. Now, there is one other thing that I did forget to mention earlier, is that the AC has been awarded the Vastrock conference, which will be held in weekend of August 9th, I think it is, down in Geelong. So we're in the process of organising that event. Did send out some information. There'll be more information coming out as we get speakers lined up and the venue lined up as well. But it's a wonderful addition to our events for this year. Thank you, everybody, for coming along tonight. I'm assuming that it is kind of clear out there. Yes, so we will be opening up the observatory. I know there's a young man up the back there who's very eager to see through the telescopes. He's like a kid in a candy store. So everyone, thank you very much for joining us tonight. We will see you next month.